So when you read this problem statement, it says when the system is released from rest, determine the angular and translational acceleration of disk A. So that phrase, when it's released from rest, means right after it's released from rest. So no time has elapsed, no distance has been traveled. So this cannot be a momentum problem and it cannot be an energy problem because the momentum requires a delta t and the energy problems require a delta x. So that means this is definitely a equation of motion problem, and if it's an equation of motion problem, that means free body diagrams. So here's the free body diagram of the block of B. There's the circle. The initial file I posted had the wrong free body diagram. This is correct now. Everything in that block is the weight, and everything it cuts through the tension T. For some reason I had the tension T on the other diagram, on the MA diagram. Doesn't make sense. And it cuts through the ground. There's a normal force, and nicely there's no friction on the slope, so there's no friction force because mu is 0. And it's accelerating downhill, and so the acceleration is going down the hill at that 3, 4, 5 angle. Okay, and so we're going to take the x components going down the hill, and so that component right there going down the hill is 3/5 WB. Okay, so taking the x components down the hill, 3/5 WB pointing downhill, the tension pulling up will equal MB going down the hill. So there it is, 3/5 WB minus the tension equals MB AB. That's equation number 1. Okay. Now we need to look at the disk, the free body diagram. I'm going to draw a little loop around there. In the free body diagram is a W. There is a normal force. Now this surface does have friction. There's a coefficient of frictions for static or kinetic. And so there's a friction force. It might be mu times n, it might not be. Depends if it's slipping or not. We've gone through this several times. And there's that same tension in the cable now pulling on the center of this disc. It looks shaded to look like a sphere, but it's a thin disc like a button. Okay, and it's MA moving and I alpha. Okay, so you take the x components to the right positive, T minus the friction force equals, on the right hand picture, MA times the acceleration of A. Okay, so the kinematics of this are such that the cable is attaching to block A and to the center of A and block B. So that means the acceleration of A and the acceleration of B are the same. They're connected to the same cable. So I'm just going to write A for acceleration. Okay, now I'm going to take moments about the center of gravity of the disk. So I've got that friction force times the radius, conveniently 1, equals I times alpha. Okay, we've gone through this several times. If it's not slipping, we don't know the friction force, but we know that A is R times alpha. If it is slipping, we know the friction force is mu times n, but we don't know the relationship between A and alpha. So what I've done here is I've just putting the equations side by side, one with slipping and one with not. Okay, so here's the equation from the block. That's the same for both. That doesn't matter. For the disk, if it's not slipping, this friction force is unknown. And equation 2, we put in for A, R times alpha. Okay, and that way we reduce an unknown. And then the solving for the moment about G, here's that equation. And what I've done is I've put all the unknowns on the left side of these equations and all the knowns on the right. Okay, if it's slipping, this equation for the block again is the same. We've got T minus MA But in this case, the friction force is known, so it goes on the right-hand side. It would be 0.15 times the normal force, which happens to be the weight, if you look at the free body diagram. I alpha is unknown, and again, now the friction force is known, times its moment arm of 1, so 0.5 times WA. Okay, so either way, there are three unknowns of the three equations. So if it's not slipping, the unknowns are the tension, the friction force, and alpha. And if it is slipping, the unknowns are the tension, the acceleration, and the alpha. Either way you solve it, and I've taught you before how to check which one is true and which one is not. Okay, that's that problem.